So when we see this word antiderivatives or antiderivatives, that word right there, or that prefix, tells us what we're doing. We're just going backwards on derivatives. We've already talked about this in terms of the graph, where I gave you the graph of already the derivative and you had to go backwards, and that was difficult. Today we're going to talk more about what this looks like algebraically. Another word we use with antiderivatives is integration, or integrals, or integrating, or integrand. An indefinite, okay, I'm going to explain more about what indefinite versus definite means, okay, but these two words, antiderivative and integration, for all purposes today, really kind of mean the same thing, all right? So number one, find a function, capital F, whose derivative is f of x equals 3x squared. So what would my function be so that when I take derivative, I get 3x squared? I mean, think backwards from a derivative. X cubed. Now, this is a lot easier for some people to see than others. So here's an easy thing to do is, if you weren't able to come up with this, you still are able to check. What's the derivative of x cubed?
3x squared.
3x squared. That's how you know you did it right. Now, could it be that I add a number here?
Yeah, let's see.
Yeah, because if you take a derivative of a number, you get 0. So x cubed plus 5, x cubed minus 3, all of those would give me the same derivative. So we have this notation here called plus c. All right? C just means a constant, a number. It is possible that c is 0, or because it's not there. It's also possible that it's a positive number, a negative number. It could be anything, really. All right? This plus c is our general antiderivative. Okay? For today, we don't know what c is. But every time we take an integral and antiderivative, we're going to put plus c. Now, I'm going to go ahead and tell you, I was that student in calculus that would have got 100 on my first integrals quiz, except I forgot plus c on every single problem. All right, every single problem I got right, except my plus c, and I failed the quiz because of it. And I remember it to this day, and that was a long time ago. All right, so don't be that person. All right, it's important that you put plus c here. It's an important part. Okay. This general solution, that is the general solution, because the specific would be if we actually find out what c is. We need a little bit more information, and we'll do that more later in the week. Okay, differential equation. What does differential mean?
You can take the derivative.
You take the derivative. So this is saying basically we already have the derivative. We're starting with the derivative and we're going backwards, okay? So this is kind of the vocabulary we're going to use here. Theorem 4.1 looks pretty messy. I'm going to read it, but then I'll explain what it means. So if capital F is an antiderivative of f on a particular interval, and capital G is the antiderivative of f on the interval I, then this is true if and only if, okay, g of x equals f of x plus c. It basically means that to have my real answer, my true general solution, I've got to have that plus c. Okay, finding the antiderivative, it's kind of like finding the x cubed. Writing your full answer has to have the plus c. So with that in mind, what does y equal if y prime is 5? 5x plus c. You gotta have plus c. All right.
So then is the general solution basically the general integral then? Same thing.
Yeah, the solution is the f of x, given the integral.
Okay.
Okay. So it says when solving a differential equation in this form, now remember dy over dx, that just means the derivative of y with respect to x. Okay, if we're given that, then it's just convenient to write this in the form of dy equals f of x dx. We put this step in here so that you understand why. If you look down here, you see all these little dx's. Why are they there? Well, how do we get from dy over dx equals f of x to dy equals f of x dx. What algebraic step happened?
Multiply dx.
Multiply both sides by dx. All right? And so, in other words, this is just saying, okay, well, if we're going to write it a particular way to answer questions about it, the derivative of y is equal to f of x dx. And if we integrate both sides, it's like opposite of taking the derivative. We go backwards, in other words. Well, on the left-hand side, we'll just have a y. And on the right-hand side, we're going to show it by this little symbol right here, which means that we're going to integrate, okay? And that's going to give us our function plus c, always plus c. All right? Dx, in other words, just means you start with the derivative, okay? That is our starting place. And so when we integrate, we kind of are basically going backwards from what we did before. So if we look at this, this says that we need to take the antiderivative of a derivative. What do you think happens when you do antiderivative to a derivative?
Comes the first.
They cancel each other out. So what you end up with is just f of x and then plus c. It's kind of like square rooting a square. Not exactly, but they cancel each other out. But the f prime is it's the derivative of capital F. It's kind of like this symbol and this symbol cancel each other out.
If you take an integration of just f, what does that look like?
We're going to do some examples. It would just be the integral of f. I mean, we'd need an example really to go any further. But my whole thing is, if you know what you have with, we're always starting with the derivative. But if I'm telling you, this is the derivative of heart. I just pick heart. It's my favorite shape. If I say this right here is the derivative of heart, let's take the antiderivative of it. You just have heart left.
Yeah.
It's just undoing what's been done. And this next rule right here is actually the same kind of thing, but in a different order. It's saying we're going to integrate, and then I'm going to take the derivative of it. So you're undoing again what you just did. All right, so I'm going to put f of x here. Don't get too caught up on when do you put uppercase and when do you put lowercase. There's a reason why I'm choosing those, but don't get caught up on that because that's really not going to affect what we're doing right here. All right, now do we need plus c? So there's two steps here. The first one is integrating. So let's say in the first step, or the inside, I do have a plus c. What happens when you take the derivative of a c? Zero again. So we don't have the plus c on my final answer. That was a really good question. All right, what do you think the antiderivative of 0 is?
A number c.
And so, yeah, and so some of you are saying 0 and some of you are saying a number. Just think, what can I put here so that when I take the derivative, I get 0? 5, 0 would count, and so would 5, and so would every other number. So C is correct. In other words, it is 0 plus C. So we're just going to write C. Remember that I'm giving you the derivative, and I'm asking you, what is this the derivative of? Okay, so this lowercase k right here also means constant, and there's a reason why we use cap C here and k here. I'm not going to get into that. That's not as big a deal as you might think it is. But when do you take a derivative and you're just left with a number?
When you have like something x.
Okay, so when you have, yeah, and this is really kind of like the one we did. Whoop, I didn't mean to go that far up. This is really kind of like 2 here. Here the derivative is 5, so the beginning function was 5x plus c. So this would be kx plus c. Think of it this way. What's the derivative of 2x plus 1?
2.
Just 2, right? What's the derivative of 10x minus 3? Just 10. So if you're given a line, basically, with a slope and a y-intercept, the derivative of that is always just the k. All right, this right here isn't, we're not really going to evaluate this, but I want to show you something here. anytime you're trying to take the antiderivative of a number times a function, you can pull that number right out in front. And this is something we're going to do a lot of later. So I'm going to mention it now, and we're going to put a pin in it. And you're going to use this without even knowing that you're going to use it. So it just means that the number can be inside or outside of the interval. It's the same. You can't do that with x, but you can do it with the number. Okay. Before we do the next one, up here, I want to talk about this problem right here. Let's say we were taking the antiderivative, or we were integrating x to the fifth. And the dx here just means that this is the derivative. Okay, it's part, when you do integral, you're going to have dx here. It could be another variable, but they just go hand in hand. All right, so think about when you take a derivative. You take the power, you multiply it by the coefficient, and what happens to the power?
It goes down by 1.
It goes down by 1. So when we do the opposite, what happens to the power?
It goes up by 1.
It goes up by 1. All right? So if I was integrating x to the fifth, it would become something x to the sixth. Now let's think about this logically. The derivative of x to the sixth is actually 6x to the fifth. And I don't want that. I just want x to the fifth. So what number do I have to put in front here? 1/5 or 1/6? 1/6. Let me explain this for everybody, and we would need plus c, by the way. Whatever number you put here is going to have to cancel out with your power. In other words, it has to be the reciprocal of that power. Reciprocal meaning, 1 divided by that number. Because 6 times 1/6 would give you the 1 that you want. It's not written there, but we know it's there. And then we would subtract 1. So what this means for our rule is we're going to do 1 over n plus 1, and my exponent on x would be n plus 1. And this right here, we are going to practice a whole bunch on the very next page. And so if this isn't really clicking with you, it could be just that you need some actual examples and with numbers in them, and that'll make that easier. For some of you, though, this makes more sense because it's a formula that you could use. All right. This right here, if we integrate a function, add it or subtract it to another function, this is a really nice rule. It means that I can do them separately, meaning I can take the integral of f of x, and then I could add or subtract that to the integral of g of x. You don't have to do them both as one thing. You just do one and then the other. We had this same rule with derivatives. Whenever we were adding and subtracting terms for derivatives, we just take derivative of term by term. We're going to do the same thing when we integrate. And again, this one's going to become, when we do an example, it's going to be more obvious than the rule right here. But we have to state that we can do this, because otherwise we'd kind of be stuck. All right, now the rest of these are trig. So let's think about this. We're not taking the derivative. Remember, we're given the derivative. So what I want to know is, whose derivative is cosine?
Sin x.
Sin x. So we do sin x, that's right, plus c. In other words, when you take the derivative of sin x plus c, you're left with cosine x. Okay, anybody feeling like we should have a negative here?
No. Yes, because you can't move it.
Okay, so in this problem, if we say take the derivative, what we're taking the derivative of is sine, and that's why there's no negative. Okay, but I know you're not the only one that's thinking there's a negative here, because I've done this enough to know. So you may think on this next one there's not a negative, but what you're doing is you're taking derivative of sine. Don't take derivative of sine. Think, what can I take derivative of to get sine? It has to be negative cosine. And then again, plus c. So think of it this way. If I didn't put this negative here, like if I cover it up here with my little pen, the derivative of cosine is negative sign, but I don't want negative sign. I want positive sign. So I need to put like an extra negative in there so that the two negatives become positive again. Okay, however you want to think of this, whatever you write down, you should be able to take the derivative and get what you started with. And so, like looking at the next one, let's forget about negatives for a minute and we'll put one there if we need it. But whose derivative is secant squared x? Tangent. Do we need a negative? No, because the derivative of tangent is secant squared and it's fine the way it is. Okay, what do you think about this next one down here? Whose derivative is secant x tangent x? Secant x. Now, if you totally forgot about all of these, then you got some studying to do. If you're really good at memorizing, memorize the derivatives and the integrals. If you're not good at memorizing, you still need to memorize the derivatives, but you don't have to memorize the integrals. Do you see what I mean? You got to do at least some of it, because there's, at this point, you don't want to have to do like quotient rule or whatever to take the derivative of secant and then think about what the integral would be. That's like absurd to do. All right, so you're going to have to at least know some of it. All right, what do you think about cosecant squared? Negative cotangent. And why do we have to have the negative?
Because cotangent,
Oh, and I put a squared there, and I'm like, it's because I'm listening.
the derivative of cotangent is negative cosecant squared x.
Yeah. Yeah, because if I take the derivative of cotangent, I get negative cosecant squared. And I want positive cosecant squared, so I gotta put that negative in there. Alright, what about the last one? Negative cosecant. So if you're like, I don't understand how she did any of that, then you need to go back and review your derivatives of your six trig functions, because this is all I'm doing is going backwards from there. Alright, if it's not the algebra that gets you, it's the trig. That's what I've learned. Okay, so let's talk about this on this. We're just going to do a few examples, and you're going to have some more to practice on your homework. So this is a polynomial. A number, an x, a power, a plus or minus, and then you just repeat. So when we're integrating this, really what we're going to do is just integrate each piece by piece. And we're allowed to do this because we said we were on the first page. So when you're actually integrating 3x to the fourth, this is how I think it's easiest to think of it. You will probably organize this information your own way as we go through this and as you work it out on the homework. Okay, what I think is, let's start with the x. The power on x right now is 4. I want it to be 5, right? We're going backwards. We're not subtracting 1 from the power anymore. We're adding 1. Now, I need to figure out what's going to go here so that when I take the derivative, I'm left with 3x to the fourth. Some of you, you have the number sense to do that. Others of you, that's confusing. So watch what I'm going to do here. I'm going to go ahead and write the number that I have, and in the denominator, I'm going to write my new power. And then we're going to check it. What is 5 times 3/5? It's just 3, and then the new power in x would be 4. So this is how you're realistically going to take the antiderivative.
Why did you not do anything with the bottom 5? I don't know. That just confused me.
Okay, so what's the derivative of that? I mean, I'm going to answer your question with another question.
X to the 4.
That's why I did it that way. I mean, you have to do whatever it takes so that when you take, that the numbers work out so that you get what you started with. So what I did is I went ahead and put the number that was already there, and I put my new power in the denominator so that they would cancel if I were to take the derivative. Okay, so let's try this again. Okay, I'm going to go ahead and put the minus. Okay, I'm going to leave a space, and I'm going to write my x, and I'm going to add 1 to the power first. That's going to be the very first thing I do. Okay, then I'm going to figure out what my coefficient should be. Okay, I already had a 5, and I'm going to put my new power in the denominator. And I do that so that when I do 3 times 5/3, the 3's cancel, and I'm just left with this minus 5.
But don't you want it to?
Okay, but you're right, I want 2 in the power. So what's the derivative of this? We do 3 times negative 5/3, that would be negative 5, and then the power would be 2. You're asking great questions. I want y'all to ask questions. You just got to work it out. Because some of this I can explain, and some of it you just have to really think through. All right, what about the last one? What do you think? Plus 1/2 x squared. And it's really easy to check. Okay? For probably about half of you, you at this point are really good at taking derivative. And this is uncomfortable. This is weird and foreign and new. So you're going to make mistakes, but then you're going to catch them. Because before I move on, yeah, don't forget that plus c. Before I move on, I am going to take the derivative of my answer. And if I don't get this whole polynomial, I messed up and I got to try again. So again, 5 times 3/5, that's 3x to the 4th. Okay, that one's good. 3 times negative 5/3, that's negative 5. Subtract 1 from the power, that's good. 2 times 1/2, that's 1. Subtract 1 from the power, that's good. And then we always got to have our plus c. Okay? You're going to make mistakes. Some of this is going to be trial and error until you kind of figure out how it's going to work out. All right. We're going to continue to practice this, but I want you to look at all the other examples. They're going to get harder. So some of you, I feel like, have checked out for the day, and you don't want to do that because I'm going to hit the ground running tomorrow. So I want to make sure that you understand how to do this. All right. It's probably going to be easier. I mean, it's definitely going to be easier if I rewrite this so that it looks like A. How can I rewrite 1 over x to the 4th?
X to the negative 4.
X to the negative 4. Okay, so watch what I'm doing. If you want a method, here's your method. If you don't want to think too hard, this is what you do. You leave a space, you write your x, and you figure out your new power. What are we going to do to our power? Add 1. So that becomes negative 3, because you added 1 to negative 4. All right? If you already had a coefficient, you write it on top. If you don't, it's because there's a 1 there. And then stick your new power in the denominator. That is the rule. That was that 1 over n plus 1. Don't forget your plus c, though.
If we forget plus c on all of them, are you going to be lenient since you?
I don't know. I got to do something so that you won't forget it. Like when my teacher took off every time I was mad, but I never forgot my plus c after that. We'll see when that comes along. I wouldn't make you fail a quiz. Just that's the only mistake you make. For sure not. I'm not that mean. All right. So let's look at C. Okay, I have not yet told you how to take the antiderivative of a radical. So we've got to make this look like something we're used to. How can I rewrite square root of x? X to the 1/2. That makes it look like a polynomial. And here we have some trig. Okay, so again, that rule about f of x plus 1 minus g of x, all that was saying, okay, let's just take the antiderivative of the first piece, then we'll do the second piece. Okay, so leave a space, write your x, write your new power, which is adding 1. When we add 1, we get 3/2. Okay, take your existing power, or existing coefficient, and do your new power underneath it. So I haven't written that yet. You could write 1 over 3/2. But what would be so much better is just to write it as 2/3. 1 over 3/2 is the same as 2/3. I don't want fractions within fractions, so yes. The reason is because today, this is where we stop. In a few days, we're going to have to do something with it. And you don't want to have to be crunching numbers with fractions within fractions, especially when you don't get a calculator. So it's better now if we just develop this good habit. Because what's 3/2 times 2/3? It's 1. So it did the same thing. All right, now, if you're not quite sure if this should be plus or minus something, well then just leave a space. The 2 I can just rewrite, because that's a coefficient. And I know this is going to be cosine x, and I know I'm going to have a plus c. So the real question is, should this be plus 2 cosine x or minus? Okay, so I got both. So if I take the derivative of plus 2 cosine x, will I get plus 2 sine x?
Yes.
No, I need that minus there, because the derivative of cosine is negative sine, the negatives will cancel. Okay, if your brain is hurting, that's good, it means you're learning. It's like when you work out, your muscles hurt. Okay, so I'm going to show you something on D, and if you feel like you're close to your limit, I just want you to watch this and then write it down, okay, because I'm going to explain. I'm about to do an algebra step that you're all going to be able to follow this, but you're going to resist it first. Okay, I'm going to take this because here's the deal. I don't have a quotient rule for integrals. I don't have that. So I got to make this look like my other problem. So watch this. I'm going to rewrite the denominator as x, since it's the denominator, and negative power cube root 1/3. All right, now this looks like a product. Still, I do not have a product rule for antiderivatives. Okay, I have a product rule for derivatives, but not this. So what I'm going to do now is distribute. My whole goal here is to make this look like a polynomial. So when I multiply x to the negative 1/3 times x to the 1, what do you do to your 2 powers? When you're multiplying exponents, you add. So what's negative 1/3 plus 1? 2/3. I'm not going to take time with the fractions. Just sort it out. All right, plus x to the negative 1/3 times 1. That's just x to the negative 1/3. All right, I have not yet taken the antiderivative. All of that was algebra. It's algebra or trig. Both of those are way harder than calculus. Okay, you can do it. The reason calculus is hard is because of the algebra. This was the hard step. Adding and subtracting fractions, surprisingly, is the hard step. All right, so this is what we're going to do next. I'm going to leave a space. I'm going to write my x. I'm going to write my new power. Can anybody tell me what that would be? 5/3. I added 1 to it. Again, I'm not going to go over how to add 1 to 2/3. Come in for tutoring if you need help on that. Okay, my new coefficient could be 1/5/3. So much better to write 3/5. Okay. If you want to write 1/5/3, that's fine, but then I want you to write the simplified version. If you want to write 1/5/3 and then write another step where it's 3/5, that's fine. Okay. New power here, I'd add 1. That's going to be 2/3. So then 3/2 would be the coefficient. Plus c, yeah. Don't forget that plus c. The plus c is good though because it's going to get you points even if you're way off on the other part. All right. Last problem, and I need to get through this before the bell rings. All right. This looks like it's impossible. Again, I'm going to do an algebra / trig step to make this a lot easier. All right. I'm going to rewrite this as sine x over cosine x, and I'm going to take one of those cosines and put it by itself. Okay, the reason I did this is because sine x over cosine x is tangent of x, and 1/cosine is secant of x. And now, this is the derivative of one of my 6 trig functions. If I didn't rewrite it, I wouldn't have even known. What is this the derivative of? Yeah, so secant x plus c. Okay. This, and on your homework, knowing your trig identities is very helpful. I would say you don't need to know all your trig identities, but you need to know the most basic ones, including the Pythagorean ones. This is why you did trig proofs. You want to know why you did trig proofs? It's so you could do integrals. That's the only reason. All right?